Hello guys, I Professor Darshan Thakur is going to explain this technique whose name is nothing but root locus. So we are very much aware of this thing. This root locus is nothing but we can say that how or the way in which we are plotting the dynamic characteristics of this control system on real and imaginary axis is nothing but plotting of this root locus, right? So with this one simple example we will go through this technique. So as you can see, the objective here is what? Plot the root locus for unity feedback system whose open loop transfer function is nothing but g of s equals to k upon s into s plus 6 into s plus 9. So while plotting this root locus, we need to follow certain design steps. Okay, so we will go through the design step number 1 for this root locus technique. So in this first step, we are supposed to determine how many number of loci we are having with us. So we are about to declare number of loci, right? So loci itself is a locus. We can say that this loci or locus is nothing but what? It is the group of point which is to be formed by satisfying a certain system equation which is denoted in this example, right? So we need to understand number of loci always equals to maximum number of either poles or 0. P indicates the number of desired frequencies at which this numerator is this denominator is being equated to 0, that is nothing but pole, and 0 is nothing but what? It is the desired frequency at which the numerator value is being equated to 0. So we need to understand how many number of loci we are having with us, which exactly equals to maximum number of either poles or 0. So what we need to do, from sake of observation, we need to determine how many number of zeros and how many number of poles we are having in this system equation. We don't have any term belongs to this s in this numerator, so we don't have any zeros, z equals to 0, right? And when we equate this denominator with respect to 0, so at that time we are coming on to this conclusion number of poles equals to 3, p equals to 3, right? Means number of loci equals to maximum number of either pole or 0. So when we are having this system equation in which we don't have any zeros, and as we are having 3 desired frequencies, those are being located at origin, -6 and -9 as far as the pole 0 plot is concerned. So we are having 3 loci, right? So number of loci equals to 3. Here I will write number of loci equals to 3. So this is the first step. Then after that, step number 2. In that step number 2, we need to plot the pole 0 plot from this system equation, right? So this pole 0 plot is nothing but, as I told you earlier, this root locus is nothing but the way in which we are plotting the dynamic characteristics on a real and imaginary axis. So this is the real axis. This horizontal axis can be treated as a real axis, and this vertical axis is nothing but what? Imaginary axis, plus j omega and minus j omega. This real axis plus sigma to the minus sigma, we can say that, right? So in this pole 0 plot, we need to show how many number of zeros and how many number of poles we are having, right? Which is to be tabulated from the system equation. So as we know, number of zeros equals to 0. We don't have any zeros and we are having 3 poles, right? So these 3 poles are being located at, first pole is being located at origin. This pole is to be denoted with this cross sign. Second pole, which is somewhere located at minus of 6, right? And this is the third pole, which is somewhere located at minus of 9. So this is step number 2. In lateral part, I will tell you what is the significance of this rough pole 0 plot. After that, we need to follow the step number 3, right? In this step number 3, we need to determine how many number of real axis loci we are having with us, right? Now one more important thing which we need to understand, or this is the basic property of this root locus, right? Which is nothing but this root locus is always or the nature of that root locus is always symmetric towards this real axis. It is never being plotted on this vertical axis, right? This is the basic property of that root locus. So by taking into account this property in this step number 3, we need to determine the real axis loci, right? So we are having certain logic belongs to this step number 3. Very simple logic we are having. That logic is nothing but what? Consider the first pole or the first zero. As we are having, we don't have any zeros, we are having 3 poles, right? So out of that 3 pole, when we consider the first pole which is located at that origin, right? So what we need to do, we need to map one thing key. What we need to map, how many number of poles and zeros we are having, those are being located to the right hand side of this existing pole, right? So as we know, to the right hand side of this existing pole which is located at that origin, we don't have any poles or we don't have any zero, right? So definitely we can say that within this region we don't have the desired portion of this root locus, means this root locus is not present in this portion, right? And when we consider the second pole which is located at this -6, and to the right hand side of this -6, how many number of poles we are having? We are having only one pole which is located at this origin, right? Means if we are having the odd number of poles and zero to the right hand side of this existing pole, definitely we can say that there will be a appearance of this root locus in between this interval, right? So first real axis loci will be what? We can say that this root locus is present in between -6 to 0, right? So the first real axis loci lies in between -6 to 0, right? Why? Because to the right hand side of this -6 we are having the odd number of summation of poles and zeros, right? So as we are having only one pole which is located at that origin, that's why this portion is being highlighted in the sense the root locus is present in between -6 to 0, right? Now when we consider the second pole which is located at this -9 position, right? So to the right hand side of this -9 position pole, how many number of poles and zeros we are having? We are having 2 poles, those are being located at origin and -6. So the sum of these 2 pole count is even or definitely it is the even. We are having 2, means we can say that this root locus is not present. NRL stands for what? There is no root locus in between -9 to -6, right? Immediately after that, one more interval we need to consider, right? Now another important thing which we need to understand, as this real axis varies from plus sigma to the minus sigma, plus infinity to the minus infinity. So always we are having one by default pole which is present at this location, that is nothing but what? Minus infinity, right? So when we consider this desired pole which is located at this minus infinity, so to the right hand side of this pole, one more time we need to map or we need to count how many number of poles and zeros we are having, right? So to the right hand side of this pole which is located at this minus of infinity, we are having 3 different poles, those are being located at 0, -6 and -9, means this root locus is present in between minus infinity to -9. So in this way, in this step, what we need to determine? The real axis loci. This is the step number 3, right? Then immediately after that we need to or we will go through the design step number 4. The design step number 4 is nothing but what? How to tabulate the centroid of loci. This is the step number 4, right? Centroid in the sense we need to determine the intersection point on the real axis, that is nothing but what? The centroid of this loci, right? So we are having one standard formula for this centroid, that is nothing but what? That formula is nothing but it is the summation of real part of pole minus the summation of real part of zeros divided by its denominator is nothing but what? The denominator will be p minus z or in some books it is being given as a n minus m. The different notations are being used to indicate these two desired frequencies, poles and zeros, right? So here what is denoted? P minus z, right? So we are having the real poles as well as the imaginary pole. Now currently in this example, this is the basic one. We don't have the imaginary poles. We are having only the real poles, right? So this centroid will become what here? Summation of real part of poles minus summation of real part of zeros, as this term will become 0 because we don't have any 0 which is present in this system equation, right? So one first pole is being located at that origin, right? So apart from that, another pole which is located at that minus of 6. So summation of real part of poles means minus 6. Another pole which is being located at minus 9. So minus 6 minus 9, its denominator will become P minus Z. Means poles minus number of poles minus number of zeros. So it will become 3. So minus 15 by 3. So as we know, 3 5 is a 15. So centroid is located at minus 5. So this is the intersection point for this real axis as far as this root locus plot is concerned, right? So this is step number 4. Immediately after that, we will go through this step number 5. Step number 5 is nothing but what? The calculation of breakaway point, right? Calculation of breakaway point. Step number 5 is nothing but how to tabulate the breakaway point, which is denoted with this alphabet called as a K. So here this K is being given by this another standard relation, that is nothing but what? It is minus d by s over n by s. Where what this d and n stands for? This is the denominator polynomial of this system equation, right? And n stands for what? This is the numerator polynomial of the system equation, or we can say that it is a OLTF, right? Open loop transfer function of this unity feedback system, in which h of s equals to 1. That's why it is being called it as a unity feedback, right? So now we will go through this standard notation, in which one more time, k equals to minus denominator polynomial will be what? Minus s into s plus 6 into s plus 9, right? Numerator polynomial, we don't have any term belongs to this s, so obviously it will become 1. Now we need to simplify this denominator polynomial. Simplify in the sense this k will become what? Minus s. Term by term multiplication, some mathematical manipulation we need to perform here. So it will become s square plus 9s plus 6s plus 9 6 are 54, right? This s is being multiplied with this parenthesis, so it will become minus of s raised to 3, 9 plus 6, 15, right? So 15s into s, so it will become 15 times of s square plus 54 times of s, right? Once we are having this desired simplified quadratic equation, then after that one more time we need to remember that this k is being differentiated with respect to s. This is the further step. In this step number 5, this dk by ds is being equated to 0 to tabulate the desired value of this breakaway point. So accordingly we need to follow this strategy in this step. So this will become what? When we differentiate this whole equation with respect to s, as this is the first order differentiation, and this differentiation result is being equated to 0. So as a result of this, it will become minus of it will become what? 3s square plus 15 to the 30, 30s plus 54s, right? Again, when we rearrange this whole term, if this 3 is being taken as a common term, and along with this minus, it is being shifted to the left hand side. So as a result of doing this, it will become s square plus 10s 54 by 3. So I think it is 18 3s are 54. So plus 18 equals to 0, right? So such type of equation we are having with us. This is the quadratic equation, right? So in that next step, what we need to do, we need to solve this quadratic equation. Here I will write, here the quadratic equation is what? s square plus 10s plus 18 equals to 0. So by using this is the usual way to solve or how to determine the roots of this quadratic equation. So this term is nothing but minus b, this is the usual way, plus minus square root of b square minus 4ac upon 2a. Right, so we need to map this quadratic equation in terms of a, b and c. So this is very simple solution. So as you can see, b minus of 10 plus minus square root of b square means it is 100 minus 4, a equals to 1, c equals to 18, right? So 4 into 18, 18 fours are I think it is 72, right? So 72 divided by 2 into a means it is 2. So square root of 100 minus 72, it will become 28. So that can be rewritten in this way, 10 plus minus it is 28 in terms of square root form. So it is 7 fours are 28. So 4 into 7 divided by 2. So that can be rearranged in this manner, minus 10 plus minus 2 into square root of 7 divided by 2, right? So when we take this 2 as a common term, so it will be as a result of this, again this 2 will get cancelled, so it will become minus 5 plus minus square root of 7, right? So here we will come to know the two roots, s1 equals to 1 and s2 equals to 1, right? So with the help of this scientific calculator, we will try to determine these two roots. It is minus 5 plus square root of 7. So it is s1 equals to minus 2.35, right? At the same time, s2 equals to what? s2 equals to minus 5 minus of square root of 7. It will become minus 7.64, right? Now next thing, what we need to do, out of this two root, we need to decide one valid root. So how to decide this valid root? So for that purpose, let us go to the step number 2, right? What is step number 2? This is the rough pole zero plot of this system equation, right? And at the same time, carefully we need to look at that step number 3, right? Now when we look into this step number 2 and step number 3, on behalf of these two roots of this quadratic equation, s square plus 10s plus 18, so we are coming on to this conclusion key, as the two different roots are nothing but what? It is minus 2.35 and minus 7.64, right? So when we look at the step number 3, the real axis loci, right? So this is the first interval in which there will be a significant presence of this root locus. That is nothing but what? It will present in between minus 6 to 0. This root locus is absent in between minus 9 to minus 6, and it is root locus. There will be a significant presence of this root locus in between minus infinity to minus 9, right? So one more, let us closely look at these two roots. So as far as this first root is concerned, that is nothing but what? Minus 2.35, right? So this minus 2.35 it will lie in between this minus 6 to 0, right? Minus 6 to 0 is nothing but what? This is the real axis loci of this system equation, in which there will be a significant presence of this root locus. That's why this area is being highlighted. So this minus 2.35, this one, this first root of this quadratic equation, definitely it will lie somewhere in between minus 6 to 0, right? As far as the second root is concerned of this quadratic equation, that is nothing but what? Minus 7.64, right? So this minus 7.64, undoubtedly it will lie in between minus 9 to minus 6, in between somewhere here. It is, this will be minus 7.64, right? But when we consider the real axis loci step in this root locus technique, so there will be no significant presence of this root locus. NRL stands for what? There will be no root locus in between minus 6 minus 9 to minus 6. So definitely this second root minus 7.64 will lie in between minus 9 to minus 6, right? So that's why are you getting my point? Out of this two roots, s1 and s2, s1 is the valid root, right? That is nothing but what? Minus 2.35. so that is nothing but what? This is nothing but the breakaway point. Now one more important step that we need to follow, that is nothing but what? Step number 6. Okay, so step number 6. Step number 6, again this is the one of the important step in order to complete this root locus plot. So in this step number 6, what we need to do, we need to determine how many number of asymptotes we are having with us, right? So asymptote, this is the algebraic term. So basically asymptote is nothing but, we are very much aware of this thing, this is the tangent which is present at this infinite value, that is nothing but what? Asymptote. So number of asymptotes equals to what? Number of poles minus number of zeros, p minus z. As we are having 3 poles and we don't have any zeros, so number of asymptotes equals to 3, right? Within the same step, this will be the first part, and the second lateral part is nothing but what? We need to determine the angle of asymptotes. Angle of asymptotes, right? So in order to determine the desired angle of these asymptotes, for that purpose this is the standard relation, that is nothing but what? 2x plus 1 divided by p minus z into 180 degree. This is the standard formula for angle of asymptotes. As I told you earlier, asymptote is nothing but what? This is the desired tangent which is present at this infinite value, right? So here one question arises in our mind, this variable x that depends upon, or that can be iterated for or one question arises in our mind, for how many number of times this x is being iterated. So that depends upon how many number of asymptotes we are having. As we are having 3 asymptotes, so this x is being iterated for thrice. Initially this x equals to 0, x equals to 1 and x equals to 2. Based upon this, this phi 1 will be what? When x equals to 0. When x equals to 0 means 2 into 0 obviously 0. So it is 1 over 3 p minus z. It is 1 over 3 into 180 degree. So as we know, 3 6 is 18. Phi 1 equals to 60 degree. The first asymptote angle. The asymptote angle number 2, in this iteration x is equals to 1. So as a result of doing this, it will become what? 2 into 1 plus 1. So 3 by 3. 3 by 3 into 180 degree. So 3 will get cancelled. So phi 2 equals to what? 180 degree. And the third asymptote angle, as this when this x is being iterated for third times, in this iteration x equals to 2. So 2 2s are 4. 2 into x. So it will become 4 plus 1 divided by p minus z, that is nothing but what? 3 into 180 degree, right? So it will become 4 plus 1, 5 by 3 into 180 degree. So that will become again 3 6 18, 5 into 6, so it will become 300, right? So these are the 3 desired angles of asymptotes. Phi 1 equals to 60 degree, phi 2 equals to 180 degree, and phi 3 equals to 300 degree, right? Then immediately after that we need to follow the step number 7. Actually step number 7 is we need to determine the angle of departure, right? But as I told you earlier, we are not having the imaginary poles in this example, right? We are having only the real poles, right? We don't have any imaginary part. That's why this angle of departure step is being skipped in this example. It is being taken into account whenever we are having the imaginary poles. So obviously the last step will be what? The intersection on imaginary axis. This will be the last step in this root locus example. So again, to know the intersection point on this imaginary axis, this standard notation is being used. That is nothing but what, this d plus k into n equals to 0, right? Here d stands for what? Denominator polynomial. N stands for, it is the numerator polynomial, and k is nothing but what? The constant value, right? So denominator and numerator polynomial, these two polynomials are being taken into account from this OLTF, open loop transfer function, right? Which exactly equals to what here? K upon s into s plus 6 into s plus 9, right? So this is the denominator polynomial and this is the numerator polynomial, right? So we need to consider these two values in this notation. So it will become what? S into s plus 6, right? Denominator polynomial into s plus 9 plus k. Numerator polynomial equals to 1. So k into 1 simply plus k equals to 0, right? Again, we need to simplify again the term by term, same mathematical manipulation we need to do. So s into s, s square plus 9s, right, plus 6x plus 9 6 are 54 plus k equals to 0. So obviously it will become, when we multiply this s with this whole parenthesis, so it will become s raised to 3, 9 plus 6, it will become 15. So 15s square plus 54s plus k equals to 0. Now another important thing, as with respect to this step number 7, that is nothing but what? To determine the intersection point on imaginary axis, one stability criteria we need to use. That is nothing but what? Already we had discussed this stability criteria, the root stability criteria. Here what we need to do, here we need to declare the root array from this characteristics equation or from this system equation, right? So in order to declare the elements of this root array, first of all we need to decide the coefficients of this characteristics equation, s raised to 3 plus 15s square plus 54s plus k. So here the highest power of s is nothing but 3. So the first element a0 will be 1, this will be a1, this will be a2, and this will be a3. Immediately after that, what we need to do, we need to generate the root array in which the highest degree of s is s raised to 3, then in descending order s raised to 2, s raised to 1, and s raised to 0, right? So in this first row we need to consider all even element, that is nothing but a0, a2, right? So a0 equals to 1, a2 equals to 54. In that second row, now here a4 equals to 0, so no need to consider that a4. Here a1 equals to 15. In that second row we need to consider all the elements, those are being located at that odd position, that is a1, a3, a5. So a1 equals to 15, a3 equals to how much? This is the constant value k, a5 equals to 0. Then to decide the elements belongs to this s raised to 1 row and this is s raised to 0 row, what we need to do, we need to follow the cross multiplication here, right? So 15 into 54, right? 15 into 54, it will become 810. Minus 1 into k, obviously k, its denominator will be this term which is located at the second row. So it is 810 minus k upon 15, right? So that can be called, it is as a b1 for sake of this moment. This will be a0, this will be a2, this will be a1, this will be a3, and this element that can be called, it is as a b1. So how to get that b1? By doing cross multiplication in between these two terms, right? So 15 into 54, 810 minus k upon its denominator will be its this particular element whose value is nothing but 15, right? So here b2 obviously it is 0, where it has nothing to do with this root array. Now we are interested for this c1 fellow, right? So c1 equals to what? Again we need to cross multiply these two terms. Here b2 equals to 0, so this whole term will multiplied with this k, and this multiplication is being divided with this term, right? So this 810 minus k upon 15 upon 810 minus k upon 15. These two terms will cancel each other. Here it will become like this: 810 minus k upon 15 into k, right, divided by 810 minus k upon 50, right. So the remaining element is nothing but what here? K, right. Now from stability point of view, as we know, as far as this root stability criteria is concerned, all the elements those are being present at this first row, this all element value should be positive. Then and then only we can say that this system is a stable system. So from stability point of view, when we consider this last element, so obviously which has to be greater than 0, right. Now the another element in which this constant value we are having, that is nothing but what? This 810 minus k divided by 15. Again it should be greater than 0. So it will become 810 minus k. It should, this whole quantity, it should be greater than 0. So 810, it should be, so we can write like this: k, it should be less than 810. 810 means it is the marginal value of this k, right. So the desired value of k for this stability is nothing but what? This k, it should be vary in between 0 to less than k, less than 810. So the k marginal is nothing but what? 810, right. Now for what purpose we are doing all these things? In order to determine the intersection on this imaginary axis, right. So how it is to be declared? By considering this characteristics equation. This characteristics equation is mapped with respect to this root array, and after deciding the elements of this root array, the marginal value of this k is how much here? 810, right. So from stability point of view, when we consider the auxiliary equation here, auxiliary equation means what? The elements belongs to the row number 2, whose power is nothing but what here? S raised to 2. So when we consider this auxiliary equation, so this auxiliary equation will become what? It will become 15 times of s square, am I right? 15 times of s square, s raised to 2. Then the lowest or immediately after this s raised to 2, the lowest s raised to power in terms of this even count will be what? It will be s raised to 0. So it will become 15 s square plus k equals to 0. So that can be rewritten as a 15 s square equals to minus of k, right. Here the marginal k, in the sense it is the marginal value of this k. Already we had tabulated the marginal value of k is nothing but what? It is 810, right. So s square equals to what? It is minus k over 15, right. How it is being tabulated? From this auxiliary equation. How to get this auxiliary equation? For that purpose, we need to consider the elements belongs to this s raised to 2 row, right, or the row in which the power of this s is nothing but what here? 2, right. So those elements are nothing but 15 and k. So when this 15 is being multiplied with this s raised to 2, so here the coefficient of k will be what? S raised to 0, right. So here 15 s square equals to the marginal value of this k. So s square equals to what here? K equals to how much? It is minus 810 divided by 15. So s equals to what here? When we tabulate this thing, so it is 810. How much it is? 810 divided by 15. So 54, right. So minus of 54 s square. So s equals to what? Square root of 54 means it is plus minus j 7.34, right. So the intersection of this imaginary axis is plus j 0.34 and minus j 0.34, right. This is how all these design steps are being completed, right. So this is the last step, intersection of imaginary axis, right. First step is nothing but what here? In that first step we need to determine how many number of loci we are having. So that is nothing but what? Maximum of p comma z. Maximum number of count belongs to poles or 0. We are not having any 0, so, and we are having 3 poles, so p equals to 3. This is the pole 0 plot. step number 2 is concerned. Step number 3, real axis loci, which is to be tabulated from this pole 0 plot, right? The simple logic for this is nothing but what, when we consider the first pole, so to the right hand side of this first pole, if we are having the number of zeros plus number of poles equals to odd count, so we do can say that there will be a presence of root locus. If we are having the even count, which count, number of poles plus zeros, if we are having the even count, so we do can say that we don't have any we don't have the significance presence of this root locus in this interval. So accordingly, these three real axis loci are being defined, in which there will be a presence of root locus in between -6 to 0. This there will be no root locus in between -9 to -6. There will be a presence of root locus in between -infinity to -9, because always one by default pole which is present at this minus of infinity at this particular frequency or at that position, right? Step number 4, we need to determine the intersection point on this real axis. The name given to this intersection point is nothing but centroid, which is given by this standard formula, summation of real part of pole minus real part of 0 upon b minus z. So it will become -5. After that, this breakaway point is being tabulated. So this is the standard relation in order to determine this breakaway point, right? So when we declare this denominator polynomial and numerator polynomial, we are getting such type of quadratic equation. That quadratic equation is to be solved, and we are getting these two roots, -2.35 and -7.64. So out of that two root, we need to decide one valid root. So out of that two root, this -7.64, where it will lie, this -7.64 will lie in between -9 to -6, where we don't have this root locus. That's why the valid root is nothing but this -2.35. So breakaway point, that can be called as a -2.35 here. Okay. Then after that, step number 6, number of asymptotes we need to define, right? Number of asymptotes equals to number of poles minus number of zeros. So 3 minus 0 equals to 3. Immediately after that, we need to determine the angle of asymptotes. So this is the standard notation to determine angle of asymptotes, 2x plus 1 upon p minus z into 180 degree, where we need to follow the three iterations in which x equals to 0, 1 and 2. Why? Because number of asymptotes equals to 3. So these three are the asymptote angles, right? Step number 7 is the angle of departure, but as we are not having any imaginary rules, so that step is being skipped. Last step, intersection of imaginary axis. This is the relation for that d plus kn equals to 0, where denominator and numerator polynomial, we need to put the desired values of these two polynomials, and we need to declare one root array from this characteristics equation, and these are the elements of this root array, in which the marginal value of that k is nothing but what, 810. To decide the intersection on this imaginary axis, we need to consider the auxiliary equation from this root locus array. So the auxiliary equation is 15s square plus k into s raised to 0, right? So by taking into account this k, marginal value of k is 810, so the intersection on this imaginary axis, these 2 points will be what, plus minus j 7.34. so these are the design steps. Immediately after that, what we need to do now here, now we need to plot this root locus, right? So that will be the last step. So we will plot this root locus here, right? So as I told you earlier, this root locus is nothing but what, it is how we are plotting the dynamic characteristics on real and imaginary axis, right? So when we consider these two axes, here I will draw real and imaginary, right? So this will be plus j omega minus j omega plus sigma minus of sigma. This is the real horizontal axis and this is the imaginary axis. So first of all, we need to declare the scale, if this is minus of 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8 and minus 9, right? Similarly here this will be plus j1, j2, j3, j4, j5, j6, j7 and j8, right? Similarly here minus j1, minus j2, minus j3, minus j4, minus j5, minus of j6, minus of j7, minus of j8, right? So first pole is being located at this origin, that is nothing but 0, right? Second pole, where it is being located according to our system equation, second pole is being located at this minus of 6, and third pole is being located at minus of 9. We don't have any 0. If we are having 0, which is to be denoted with this bubble sign, right? So after that, as we know, this portion is being highlighted, which is present in between this minus 6 to 0, because there will be a significant presence of this root locus in this interval, right? Similarly from minus of infinity to minus of 9, right? According to our step number 3, here as you can see, this is the step number 3, real axis loci, right? So accordingly it is being taken into account. After that, what we need to do, as we know, the centroid of this loci sigma c equals to how much? It is minus of 5, right? So consider this is nothing but what? The sigma c equals to minus of 5, right? With this sigma c, with the help of protector, we need to plot the angle of asymptotes, right? As we know, alpha 1 equals to how much? Already it is being tabulated 60 degree, phi 1 equals to 60 degree, phi 2 equals to 180 degree, phi 3 equals to 300 degree, right? So these angles are being taken into account with the help of this protector from this centroid. As I told you earlier, so centroid is nothing but what? The intersection point on this real axis, right? So with the help of this protector, when we consider the first angle, that is nothing but what? 60 degree. So this will be somewhere like this. With the help of protector, actually you need to consider this angle. Phi 1 will be the 60 degree. The second asymptote angle is how much here? It is 180 degree. So when we consider this protector here, so from this point, this will be the second asymptote angle, that is nothing but what? Phi 2. So this total angle will be what? This will be 180 degree, right? And third one will be what? Third asymptote angle is nothing but 300 degree. So with the help of this protector, somewhere it will lie like this. So this will be 300 degree. Phi 3, 300. So that can be treated as a asymptote angle number 3. This is asymptote angle number 2, and this is asymptote angle number 1, right? Then after that, as we know, the breakaway point, which is tabulated in step number 5. So the valid breakaway point is how much here? It is minus 2.35. So we need to consider this breakaway point. This will be lie somewhere in between these two locations. So this will be breakaway point, k equals to how much? Minus 2.35, right? So with the help of this breakaway point, step number 7 says that the imaginary axis intersection points are nothing but, those are nothing but plus minus j7.34, right? So with the help of this breakaway point, plus minus 7.34, so this will be plus j7.34 somewhere, and this will be minus j7.34. So we need to draw this freehand curve like this, which will pass through this breakaway point, and it will intersect it will intersect this imaginary axis here, that is nothing but what, plus j 7.34. and as far as the lower part is concerned, so with this freehand sketch again it will intersect this imaginary axis on minus j 7.34 and plus j 7.34. so in this way this root locus plot is being completed. So I just hope you understand all these things in this session, right? So hopefully in next session we will try to learn how to plot the body plot, right? So thank you very much.